Hello everybody, my name is Aditya Sharma. I am a faculty member in the Department of Physics here at IISER Bhopal. This is part 2 of a two-part course on mathematical methods in physics. This is pitched at the level of third year undergraduate students who are majoring in physics. So in fact, our own BSMS students in the third year have taken both these parts. It is part of one of their core courses, and so the idea behind these courses is to help build a strong foundation for students who are going to major in physics, and potentially some of them may go on to continue to do a PhD in physics. Although the material is geared towards physics students, so the content is quite general, and students in other applied sciences which involves mathematics would also benefit from taking this course. Engineers for sure will find a lot of useful content here, and even mathematicians may find the perspective that is offered here useful. So this is part 2 and is a logical follow-up to MM1, and yet we have tried to make all the topics as self-contained as possible, and therefore it's certainly possible for a dedicated and sincere student with initiative to start with MM2 and pick up some material, some gaps in their understanding they would be able to fill in as they go along and still benefit from and do well in MM2. And so it's possible that they may go on to formally do MM1 in the next semester, or it's also conceivable that they just pick up all the required material in parallel, doing both MM1 and MM2. So the broad plan for this course is as follows. So the major chunk of this course is going to be devoted to complex variables and applications. So about half of this course is going to be related to this topic. And we are going to cover concepts of differentiability, analyticity, contour integration, residue theorem. So lots of examples would be worked out, and so the theory also would be built around these examples. So that's the general philosophy of our approach, is to present examples and encourage students also to solve lots of problems. Sometimes go beyond the homework that is given and find more example problems. The more problems you solve, the better you become. That's the general philosophy of this course. And so largely it's a physicist course. So the examples would be geared towards potential applications in physics. And so we'll also try and indicate what the theory is, right? So the second half of this course is going to be roughly split evenly between orthogonal polynomials and partial differential equations. Orthogonal polynomials, we will cover Legendre polynomials, Laguerre polynomials, Hamid polynomials, and also spend some time on Bessel functions, which also belongs in this box of interesting functions with similar properties. And then we'll move on to partial differential equations, where we will cover standard PDEs which are encountered in physics, like the Laplace equation, the diffusion equation, heat equation, wave equation, and so on. We'll also briefly indicate some general aspects of the theory, covering elliptic PDEs, parabolic PDEs, the classification involving the third kind being hyperbolic PDEs, and so on. But largely this part is going to be about finding physics related examples and solving them, and it's mostly about giving you an idea of how the techniques are used for physics applications. So the references are, there's quite some overlap with the references we suggested for MM1. Both Mary Bowa's book and Asken and Weber's book are standard references, particularly undergraduate friendly textbook with the theory built from scratch without assuming too much background for the student, and also lots of exercise problems, example problems. Definitely a book that students would benefit from consulting. An excellent textbook to refer to is the one by Professor Balakrishnan. Again, it's a bit more advanced than Mary Boaz's book, and so uh, at this level, perhaps it's useful as browse material and also to dip into some unique insights that he's able to offer, and also for uh, examples and extra exercise problems. Another excellent source is the two-part series of books by Professor Joglekar, both of which we will dip into in this semester's material. This orthogonal polynomials, where his treatment I find is excellent. So there's this constructive approach he builds on, and many of the properties of the specific sets of polynomials are derived later on. First of all, we have this general framework, and so we will try and closely follow the treatment in Joglekar's book. Also, we will benefit from looking at his book for complex variables. But there is this book by Churchill and Brown, which I particularly strongly recommend for complex variables and applications. It's an excellent book. Everything is explained in a lucid manner. Examples are given. It's also a mathematician-friendly book, but also a book which physicists or students training to become physicists will benefit from. So excellent book to refer to for complex variables. Our treatment is certainly going to be influenced by both Joglekar and Churchill and Brown. We'll also look at A.K. Kapoor's book, which is an excellent source for lots of example problems, and also exercise problems which are collected in an extremely systematic way. There are it's graded according to difficulty. It's also organized into different boxes for students to work out problems of different level of difficulty, but also of different types and subtypes and so on. So it's an excellent source for the serious student. If they're interested in mastering complex variables, they'll definitely benefit from taking a look at A.K. Kapoor's book. There are also lots of dedicated textbooks on PDEs. One book I can mention is the one by Shankara Rao, again because it has lots of example problems. So at this level, we learn best by solving lots of problems, working out, looking at lots of worked out example problems helps. Therefore, books like Shankara Rao's book are useful at this level. So this is broadly the plan of action for this course. To get the best out of this course, I would recommend that you watch all videos on time, do the homeworks. There will be weekly homeworks given, work out all the homework problems, take it seriously. The homeworks are supposed to train you for the final exam, but also they're supposed to, help you learn the topics covered better. And I will also encourage students to, push themselves a little and find more problems from any of these sources mentioned here. But also, the internet has plenty of resources from where you can pull out more, interesting problems around, themes which are covered here, and you will definitely benefit from solving lots of problems. So yeah, so to get the best out of this course, watch all videos on time, do all the homework, put in some extra initiative, and solve more problems, and just have fun. So hopefully, this intro video will inspire you to register for this course. Take it up seriously and also have fun. Okay, thank you.